before, is mass transfer. I'm going to spend a fair amount of time here because this, again, is kind of stuff that we have to have in our brain so we understand what it means to be diffusion controlled so that eventually we can understand what it means to not be diffusion controlled as far as things go. So we were just talking about like the rate of reaction, right? And it still hasn't changed since last we talked. You know, I think it was yesterday I put up that diagram where I said there are all these sorts of things that can have rates, right? The rate of the reaction, you know, depends on a variety of factors, right? It can depend on mass transfer. It can depend on electron transfer. I'll speak in absorption in this lab. Like out the text, but and most of the time in electrochemistry, they assume that electron transfer is assumed to be fast compared to mass transfer, and so most of the time they assume that mass transfer is the rate limiting step. And so again, most of what you see in a textbook is going to use that as the assumption. Again, the definitions we learned yesterday about being reversible and following the Nernst equation was our practical definition, right? That all goes to the assumption that mass transfer is limited. So if you know, if that's not true, you're probably not going to have a reversible reaction. Okay, so there's 3 modes of mass transfer that I skipped when we did chapter 1, because I said I'd come back to them when we did this chapter. And so the 3 modes of mass transfer are, actually most of the students will know these. What are they? The easy ones first. Diffusion. Next. 2 more. We talked about one yesterday. What did you say? Migration. We talked about migration yesterday, right? Because we talked about the electrochemical potential and the fact that things are in an electric field if we're applying a potential. All right, so we have migration. What was the last one? Convection. Convection, all right. That's the one you usually don't talk too much about this setting, but convection is sort of always there. Right, so, all right, so let's define that then. Diffusion is movement of a molecule due to a gradient in chemical potential. So yesterday we defined chemical potential. And chemical potential has a concentration term in it, which everybody's used to sort of see. So you probably would have defined diffusion as like moving according to its concentration gradient or something like that. And the real thermodynamic definition is moving according to a gradient in the chemical potential, but they're not all together, like incongruent, which is why we often say the concentration one instead of the super correct one. But yes, things are going to move according to a gradient and chemical potential. All right, so migration, which we talked about yesterday, is movement of a molecule. And in this case, it's got to be a charged molecule in an electric field. So remember I said we see migration in electrophoresis and other things too, not just electrochemistry. And so it's moving in some sort of gradient of electrical field. And then convection, there's really 2 forms. So it turns out that in electrochemistry, we like to stir a lot. So there's sort of naturally occurring convection, right? And so naturally occurring convection has to do with temperature gradients, right? So you get temperature gradients. These actually cause a change in density and cause things to move. So temperature, but most people kind of associate convection with temperature gradients. But I think if you just thought of that and said, well, we don't really do that in electrochemistry, we don't really care about that, you're wrong, because we create our own convection a lot in electrochemistry, and that is we stir. And so when we stir around the solution, what are we doing? We're helping the analyte get to the electrode surface faster. They have given stirring a fancy name in electrochemistry. I have to admit, I didn't remember this fancy name from my electrochemistry class. I had to look it up once. I was like, they're talking in this paper about how they're doing this experiment under hydrodynamic transport conditions. I was like, I don't know. Essentially we see hydrodynamic voltammetry or hydrodynamic this, and it just means they're stirring. So, don't let it confuse you. It's no big deal. But let's think about our experiments. Do we have any convection in our experiments? Yeah, so I have at least one vote for yes. Anyone else want to go with that, or you know? Let's think flow cell. Is there convection in a flow cell? I'm getting a lot of dots, right? It's not stirring though, right? So not the traditional this, right? But I'm flowing. I'm accomplishing basically the same thing as stirring. I'm flowing my analyte by it, right? It's not just diffusion that's getting it there. I'm pushing my analyte to the surface. So yes, I had convection in a flow cell experiment. Brain, maybe not. Although some people argue for lots of temperature gradients in the brain, but certainly you're not flowing like you are in your flow cell. So I think a lot of times people mistake that. They think that, I'm not stirring. Well, you're not stirring, but you are flowing. So it accomplishes about the same thing. So yes, flow cell experiments, all hydrodynamic experiments. You're doing hydrodynamic voltammetry, whether you do it or not, as far as that goes. Okay, so when you stir, I think almost everybody who's ever been in a class with me has seen this diagram before. If you have this as your electrode surface, when you stir, you create turbulent flow. That's supposed to be turbulent flow, right? Where things flow every which way around in solution. But once you get close to the surface, it turns out you don't quite get turbulent flow. The closer and closer you get, the more things just kind of run on parallel by. So this is called laminar flow. So laminar is parallel flow streams. You get laminar flow in HPLC when you push down the tube. It all pushes and kind of goes in parallel. So out here, you get turbulent, but closer to the electrode, you get laminar flow. And then really close to the electrode, again, this is, another thing that's kind of like our Nernst thing. We get what most people refer to as delta, which is called the Nernst diffusion layer. And in this delta area, you must diffuse. So the closest that stirring can bring your molecule is basically right there. Stirring can't bring your molecule because of the frictional forces quite all the way to your electrode. So stirring gets it this far. It could travel in laminar flow. And from here, then it has to diffuse. Hence the name, the Nernst diffusion layer. And so even when you're stirring, there's an influence of diffusion. But what it does is it constantly puts stirring constantly brings new molecules, to that spot that then can diffuse across and be seen at your electrode. So it's not the stirring removes all diffusion, it just brings them closer. If you don't have stirring, then you have an electrode. And if you turn on the potential right, you'll start off with a diffusion layer, and this diffusion layer then will just grow and grow and grow, and that's kind of like a depletion area, where basically I don't have any way to get, stuff right near the electrode. It's taking a long time for things to diffuse in. So this diffusion layer, again, with no stirring. This diffusion layer grows in time. So that's important, as I said, because we'll see this come, quite frankly, in some of the equations. That's why I always seem to end up showing this diagram, because it shows you where the delta comes from that comes back in some of the equations. Okay. Right, so if we were here, I have two sets of notes today, this may be a little bit confusing, but I think I can do it. I'm too lazy to make a new one set. So if you were here, right, if we were right there, what would be our velocity? Right, well, our velocity that we could go if we were in the Nernst diffusion layer, right, would be equal to whatever my diffusion coefficient again. We're always doing the same Faulkner reaction. So the O, diffusion coefficient of O, times basically whatever the concentration gradient is. And again, x is equal to 0. Again, it's just always the electron surface. So the velocity is going to be equal to basically whatever the concentration gradient is. Remember, that's what's driving, basically, diffusion times the diffusion coefficient, how fast it can go. Turns out that the velocity here ends up being, so I'm going to define a term here. So C0 prime is going to be the bulk solution, meaning, sorry, the little star, is going to be the bulk solution, meaning, you know, and out in the bulk I've got, you know, 20 micromolar dopamine or something like that, right? And we never, we're going to assume we never use up, you know, enough to really change the concentration. So we have the bulk, and then, right, if we wanted to see what's the concentration gradient, well, the concentration gradient, right, is whatever the concentration of O is at the surface. And then what's the distance that we're going? Well, I told you the distance over here, we call it delta, right, is the Nernst diffusion layer, so we'll call it this. And most of the time, right, quite frankly, we're going to drive the concentration at the electrode surface to be 0, right? Meaning if it gets there, it's going to be used up. You know, as long as I have a high enough potential, it's going to be used up. And so oftentimes this will be 0 as far as that goes, right? And this is all equal to but nothing else today. And so if we all, you know, put that together, right? The current, then, if we're stirring, the current is going to be equal to NFA D0 over delta times. I find the term in the star. All right, so, right, so this, again, sometimes people will say, I don't know how to calculate delta, so they'll call it, the book calls it M, and then it's going to call it for mass transfer coefficient. Basically, it's just D0 over. So, if you want to combine those two together, fine. So you can see then, again, yesterday I told you that I never, ever, ever want to hear you in a presentation equivocate over whether electrochemistry is quantitative. Meaning, you know, current is related to concentration. Okay, now your experiment may not be working out perfectly, but electrochemistry is, in theory, quantitative. And you should always start there before you explain why your experiment didn't work. This is the kind of simple sort of equation that we get that tells us electrochemistry, the current we get should be dependent on the concentration. And there's just a whole lot of constants kind of that go into it. Okay. Okay, so let's go back. So now that was all the chapter 1 stuff on mass transfer. That was the easy stuff. Now we're going to go back and do it again, but we're going to do the chapter 4 stuff. We're going to talk a little bit more in depth about like real things. So anyway, just a little repetition, but not too much. Okay, so we just did our modes of diffusion instead of mass transfer. And so we said we have diffusion and migration. And I told you diffusion was based on a gradient of chemical potential. I said migration was dependent on electrical potential. And remember yesterday we defined electrochemical potential as basically chemical potential plus a term that took into account the potential gradient you applied. So if you look at diffusion and migration together, these are sort of dependent on electrochemical potential. So again, this gets you sort of the concentration, the chemical potential term. This one gets you the electrical potential term. So you can start to write lots of lovely equations that have to do with electrochemical potential, and you're kind of combining these two things together. How much it wants to move because of the chemical gradient, how much it wants to move because of the electric field. And so both of those kind of come into play. And so if we get a movement, this movement that we get is called flux. And so the flux of, we're going to call it molecule J in this case, is proportional to whatever the gradient is of the chemical potential. So whether or not something is moving, it depends again on a gradient of electrochemical potential. So if you really understood separations, that everything moves again in separations without an electric field, everything moves based on a gradient of chemical potential. As I said, all we've done is done an electric field, which basically makes it electrochemical potential instead. Turns out flux, we don't always like to think in terms of flux, is the better, the I over NFA is the better kind of fundamental term, I'll put it that way, than current. But we really like to measure current, not flux, so we almost always talk in current. But you get to a really fundamental kind of person and they like to talk flux, because flux is what comes out of diffusion equations. Okay, so so we have, like, this is proportional, right? And so we have some sort of proportionality constant. In this case, the proportionality constant happens to be a minus sine theta because of sign conventions. Concentration of J times diffusion coefficient of J over RT. That's the same equation, but instead of taking out the proportionality, you know, what's the proportionality constant of that? So now it's not proportional, it's equal. This is pretty much, if you sort of just have linear mass transport, this is pretty much the equation. Just take that minus the T, RT, and you, instead of this funny delta, what you just do that. Okay, so that's sort of relating back to flux. Okay, but we haven't really done anything with a convection term. So like I said, you know, we can put both migration and diffusion kind of into those two terms. And so if we really wanted to add convection, we could add. So if we want to add convection, we just need some sort of concentration, and then some sort of velocity. We're going to call it velocity of flow here. So think flow rather than convection. So we could add a term of flow. So as I said, this term is both migration and diffusion, and that term's flow. and it still doesn't look like anything you know how to really solve. I don't know if I could really do that. Okay, so it turns out that you can, again, I don't know where I'm going to end up here, go to one of the sort of famous electrochemistry equations. So this is called the Nernst-Planck equation. Nernst-Planck, pretty well known. This is their equation for mass transport. And so it turns out that you could split this term up, right? So I told you it was both migration and diffusion. If you split it up, you can get a diffusion part. And so the diffusion part is minus d, diffusion coefficient of J, times the concentration gradient of J. And you get a migration one. This should look familiar, sort of from the electrochemical potential. So Z again is charge. Migration is going to depend on whether it's charged, how fast it goes in the field, times F over RT. And this one ends up having a diffusion coefficient D times J. And then it's dependent on, this is again no potential gradient. So how much your electric field, changes over the distance. All right, so this is, again, that's your diffusion term. This is your migration term. And then we can get some sort of flow term. I don't know what changed. So again, that's called the Nernst-Planck equation. And you could